As you can see, there's a hint here. I put add a file size condition to find large packs, for example, add file size over 300,000 bytes. You can, in fact, add a file size limit to make it only look for small files, like file, small, like one rule files or files containing a few rules, and not look for large packs. But it's up to you how you want to do it. So today I want to continue with talking about strings and options that you have for string matching in YARA rules. So if you remember this YARA rule from yesterday, we talked about the meta section and different parts, different fields that are recommended by researchers to add in the meta section. And as you remember, this section is not a mandatory section; it's optional, and any field that you add is just for like extra information. For other people that look at your YARA rule, or for yourself when you want to check your rule later. Um, Today, let's talk about the strings. So if you remember yesterday, I mentioned that it's good to put comments in the YARA rule, like when you are doing programming and you write a code, and put some comments to make it more clear. Here in this YARA rule, you can see that our strings, the A1 and A2 strings, and these are hexadecimal values. With hexadecimal values, we need to put them in the curly brackets. And with ASCII strings, we need double quotations. We will check them later. But here, because it's not very easy to look at hexadecimal values and understand what was this string, um, the comment above shows what the actual ASCII string was that we decided to put the hexadecimal value of it um, in the YARA rule. So this is just um, for having extra information and making it more clear for like later reference. Now let's talk about something else that's very important in YARA rules. Let's talk about ASCII strings and Unicode strings, because if you want to look for ASCII strings, your rule is only checked, the strings inside your rule are only checked against ASCII strings inside the files. And if you look for Unicode strings, they're only checked against Unicode strings. And there's a specific identifier that you add at the end of your string to let the YARA engine know that this was an ASCII string or this was a Unicode string. And this one here, the example string that I put here for you, this is Hue. Hue is a very common hex editor for Windows operating system. It's been used for many years by researchers because it has lots of functionalities that are quite useful. But anyway, I just put it here for making it clear how the Unicode string and ASCII strings work. As you see here, the hexadecimal values in the ASCII string at the bottom part. For H, we have 48 as hexadecimal value. For I, we have 49. E is 45 and W is 57. And in the Unicode string, you can see that the same hexadecimal values are at the lowest how to say, a least significant byte of each byte, and the same this is the same hexadecimal value, and then we have 00 in the most significant byte. Um, so this is how ASCII is converted to Unicode. And of course, with Unicode strings, we have more options, and there are like strings from characters from different languages and also other extra like special characters in Unicode character set. Now let's talk about different identifiers that work with YARA strings and help to make it more specific or sometimes more general when YARA wants to look for these strings inside the file. Okay, so first thing, the default form is just a string inside the double quotation. And this is the default, which means this is ASCII encoded and it is case sensitive. So if you put my string like this, if there is a my string inside the file with capital M, it's not going to be matched. Next is full word. When you put full word identifier at the end of the string will match only if it is delimited by non-alphanumerical characters. So what this means is that it's not part of, it's not a substring of a string. It's the full string inside the file. Then we have no case. Sorry, then we have no case. No case makes it case insensitive. So you make it, as you see here in this example, I have put it like a camel case phrase with capital M and capital S. And with the no case identifier, it will match with any sort of like case options inside the file with all lowercase or uppercase or anything, any combination. Then we have void. This is also very useful. Void is used for the Unicode strings. This is, as you see here, used to search for strings encoded with 2 bytes per character, like Unicode strings. So if you are looking for a Unicode string, my string in a Unicode form, you have to put void. If you are not sure if the string is going to be ASCII or Unicode, you need to have both options. Like you need to have it once without the void, identifier, and one time with void identifier, or you can combine them in the form of the next one. As you see, the void ASCII. This means that it can either be void like Unicode or be ASCII string. Also, you can combine other identifiers with each other. You can add like different things, like the next example, you can have full word, ASCII, void, no case. This means that it has to be full word. It can be either ASCII or void, and it should be case insensitive. Also, the last two, XOR and base 64, these are two like more specific identifiers that are used to match the string even if it's encoded um, in the base 64 format, or for the XOR, the string will be checked against um, every possible way of XORing the string with only 1 byte character, 1 byte XOR key. So if you know that one string, like for example, this string can be like a server domain of a malware, you are sure that this string is going to be XOR encoded inside a file with just 1 byte key, but you don't know what that 1 byte XOR key might be, or you have seen several examples and the XOR key is changed in every sample, you can use the XOR identifier like this and use the plain text a string to make sure that it is going to be checked um, against every form of the XOR encryption with 1 byte key. Okay, now let's talk about the basic conditions. This is the same rule as we saw already. With the conditions, you can see the first part, which is a very important part that checks the header of the file. This uint16, this means that the first unsigned word bytes of the file, and the 16 here means that it's the first two bytes. As you see here, we are trying, and this 0 in the parentheses is the offset of the file. So you are asking for offset 0 to have this value, which is 5A4D. And 5A4D is the magic string at the header of Windows executable files, portable executable files. The ASCII representation is MZ. You might be more familiar with that. Also, we have and file size lower than something. And also, we have another condition that says any of the strings starting with A. So as you see, with the and, with these two ands in between these phrases, we have just one uh, big condition. That's why we call it condition, not conditions. It's just one condition. You can use and, you can use or, you can use other stuff like we saw yesterday with like all of them or any of them in the strings. Oh, sorry. I just noticed that there are some questions in the chat. Uh, what's the difference between the first and second? Rahim, can you make ask your question again? Which part you were talking about? Sorry, I missed your it's the previous slide. Okay, let's go back to the previous slide. So this one. Okay, the first and second. So the second identifier, the full word, this means that we want this to be a full string. We don't want it to be part of a string. Like for example, if we have my string in a file and we only look for str with the full word identifier, it's not going to be matched because str is just a sub a string of my string, something like that. Makes sense? It needs to match the exact same string inside the file. So as you see here in the description here, I put the string will match only if it is delimited by non-alphanumerical characters. So this means that it has to be a full string inside the file. We will try to use a tool and extract all the strings from different files to see what this means. What does it mean to have a full string in the file, and what are like different strings? Exactly. Thanks, Sasha. Yeah, it's a full word match, not the partial word match. Okay, and there is another question. Why does Unicode? Yes, already explained that. Okay, let's talk about the conditions a little bit. Just excuse me for a second. Okay, so talking about the basic conditions. First of all, it's important to check the header sometimes. If you are dealing with binary files or if you are dealing with executable files, for example, PE files, which are portable executable files for Windows operating system, they all start with the 5A4D that I already mentioned in the previous slide. Also, we have other examples down here. You can see for macOS executable files or for ELF files. The first one here with 0x46 4c45 7f. This is for ELF files, which are executable files for Linux operating system. and then the next four, these four 0xFEEDFACF or 0xCFFAEDFE or the other two. These are all sorts of executable files, like magic headers of executable files that are found in macOS executable applications. And as you can see, because these are like 4 bytes, we have uint32 at offset 0. You can actually change this offset if you are looking for something else. Like for examples, we have, imagine you have a specific malware that modifies like the header of the executable file, but you know that there is another magic value inside the file, like in offset 50. You can use that magic value at offset 50 or anything else. This is just the offset of the string or of the exact value that you want to be matched. Also, there is something else here that's actually quite useful in some cases. Um, we have a string count, which is stored in a variable that is shown by the pound character here. Um, you can see that this means that we need to have exactly 5 times of the string A in the file, or we have more than 7 times the string B in the file. This is quite useful in many cases. We'll actually see an example in one of our exercises later. Also with the file size, you can use the actual bytes, number of bytes, like file size greater than 520, 512, and file size less than something, or you can actually say file size less than 5 megabytes, gigabytes, megabytes, whatever you want to use. These are all defined in the YARA engine. Okay, before moving on to our first exercise today, I want to ask if there is any questions about the strings, about the conditions that we have learned so far, and then we can move on to our first exercise. You can unmute and ask your question, or you can put your questions in the chat if there is any questions.
Hi, Nushin. Yep. I was looking at the previous slide. You mentioned something about MZ at 0 versus the uint 0. Yeah, you mentioned this is fast or slow. This is good or bad. Any indication of the difference in the speed for the scanning?
Yes, sorry, good point. I actually forgot to mention that. So there are two ways to look for example, the magic value of MZ at the beginning of the P file. You can either use uint16 offset 0, the hexadecimal value 0x584d, or you can define a string with the MZ characters, and then in the condition you can ask for MZ to be found at offset 0. And as so here, this is the good option, this is the bad option. This is faster, and it's only because of the internal processing of YARA engine and how it parses the files and then looks for strings. So with the strings, the YARA engine needs to extract all the strings first and then match all your string options against the strings that are extracted. But with the first option here, you can see that there is no parsing, there is no extracting anything, and your engine only needs to look at the offset 0 and look and check it against the value that you have provided. That's why that's the faster option, and the second one is the slower option. Did that answer your question?
Yes, it did.
Okay, great. Okay, guys, let me actually share the link of the files and um, tools that you had to download. This is the same link as yesterday. So if you have downloaded this and extracted this yesterday, you don't need to do anything. This is only for people who have not joined yesterday or missed the first part or missed this part of the training yesterday. So let me find, give me a minute, let me find the link. This is this link has a zip file. You extract it on your host machine. There is no malware, there is nothing malicious inside this directory. There are a few tools that you can use and we are going to use today. There's actually the um, YARA engine for Linux and for no, sorry, for Linux was not there, just for Windows. For Linux and for Mac OS, I'll show you how to install YARA on your system, and then we can proceed and work on the samples. Uh, okay. So from the link that I shared, you can download the files, the exercises and tools, and you can install YARA on your systems. You can look at the documentation. I'll share it here. Some of you have asked for the platform that we are going to use and how we are going to proceed with the exercises. So please download the files and use the second link to install YARA on your system. It doesn't matter what the platform is, if it's Mac OS, it's Linux or Windows, you can work with it with YARA. Okay, now let's talk about a tool that we use to extract the strings from a file. Um, Mostly used on binary files. If you remember yesterday, we worked a little bit on the files. Like for example, we were trying to catch YARA rule files, and YARA rule files are text files. They're easy to read. You can just open them in a text editor and look at the strings inside them. But with binary files and executable files, it's it's not that easy because these are compiled files and these are binary files. But most of the times when we deal with malwares, um, there are unique characteristics in files that the majority of these characteristics are hidden inside the strings that are that are present in the files. So what we do, we usually extract the strings from the file, look at the strings, find unique strings. It might not be easy for you if you are not familiar with this process to spot unique strings or like unique combination of strings, but we will try to work on easy examples and exercises to make sure that we completely understand what we are doing and how the YARA rule is going to work on our samples. So the strings, if you use Linux or Mac OS, you have the internal strings utility on your system. You can just use it with the keyboard strings, and you can give it the file, the exercise 2 file that you are going to work on. And you have downloaded it yesterday or maybe today from the link I provided. Um, these strings with no options gives you the all of the ASCII strings inside the binary file. You can then look at them and try to find something. Also, if you are looking for some specific strings, you can use grep on Linux or Mac. You can pipe the output of the strings to grep, and with -I, you make it case insensitive, and you give it the specific string that you are trying to find inside the strings. Also, the last option here, -el, this gives you the Unicode strings inside the file. So make sure that when you are looking for a specific string, or when you are trying to find unique strings or interesting strings in a file, you check both options, ASCII strings and Unicode strings. So this is for Linux and Mac OS. And for Windows, I have shared with you the strings tool. You just extract it from the zip file and use it like this. You give it the file, the exercise 2 file, with no options. It gives you all the ASCII and Unicode strings. But if you remember, with identifier void at the end of the string in YARA rule, we need to know if the string is ASCII or if it's Unicode. Um, Otherwise, we have to use both words, both identifiers, ASCII and void. So it's good if you use -A to only get ASCII strings first, and use -U to get Unicode strings next. And similar to Linux, you can pipe it to a similar utility that works on Windows, which is findstr. And the \I makes it case insensitive, and then you can look for some specific string here, or you can even use regex sometimes, but it's a bit more complicated. Like for Linux, you need to use egrep and other stuff. So this is what I suggest you do. You check if you have Windows or Linux or Mac, just use the strings, look for all the ASCII strings, look for all the Unicode strings, and then try to find that specific string that you are looking for. And then when you find that string, just use it in the YARA rule and try to work with it. So this is our exercise that we are going to do. We are going to work on. First step, find the string. This exercise, this example, this is a module that belongs to .NET environment. We want to find the string inside the file that shows that this file belongs to .NET environment. And when you find that string, we want to use it in a YARA rule to find other modules of .NET environment inside the collection directory that you have. And you should be able to find 4 files in total. So if it's not clear, let me know. I'll make it more clear. If it's clear, please start working on the exercise. I guess maybe 10 minutes should be enough. Um, I'm here. If you have any questions, let me know. So yeah, let's start. Please let me know in the chat if you have some ideas how to do it. Um, if you have found the string, if you have started working on the YARA rule, or even if you don't have any idea how to work on it, again, let me know. I can explain a bit more. So anyone has any idea so far? Has anyone found a string that has reference to .NET environment inside the file? Or before that, have you managed to extract the strings from the file? Okay, so I see some of you have extracted the strings. So try both options. Try ASCII strings and Unicode strings. So for those of you who have managed to extract the strings, do you have any idea how to look for a string um, that shows .NET environment? Oh, that's good. Uh, Someone has found a string that uh, has a reference to .NET environment. Let's see if you can use that string in a YARA rule to find other modules. Um, for the rest of you, please try both options. Please try to extract ASCII strings and also Unicode strings, and try to look for something uh, that has a reference to .NET environment. So I hope it's clear how to use the strings and how to pipe it to grep or find a str. Is that part clear? Anyone has any issues with that part? Okay, I guess that means that's clear. So try piping it to grep or find a str based on your platform, and try looking for example, .NET, string .NET. So anyone else has found the string? So the string that you want to find is already in the chat. One of you guys have found it. So that's a hint. Try to look for that string inside the file. And if you find it, make sure that you understand if it's ASCII string or it's a Unicode string, and then create the YARA rule. A few more minutes, and then we can work on it together. So any luck, guys? I really like to know if you have problems working with the strings or YARA rule, or you have managed to do it. Just let me know. We are here to learn. Um, just want to know where you are stuck. Okay, let's work together and see how we can do this exercise. Actually, I know at least one of you have found the string and maybe wrote a YARA rule that could catch the files from the collection. Let's see. I hope I'm not pronouncing your name wrong. Gian, is it?
Yep. You
Okay,
can just call me
great.
JH.
Okay, JH.
Yep.
If it's okay with you, I'll stop sharing my screen. You can show the rest of the group how you found the string, and then how you wrote the rule, and maybe I can show my rule after that.
Yeah, sure, no
Sounds good.
problem.
Okay, great. You are on mute, JH.
Okay. Yep. Can you see the screen? All right, great. So what I did was actually to run the strings file. Okay, let me see whether I can just do this. All right. So what I did was to run the strings on exercise 2 a few times. So the first time for this, I think it was all ASCII. I didn't manage to get all the information that I needed. All right, a lot of the information within is interesting, but not really relevant. So the second time that I actually run the strings, uh, is with the EL switch, and that actually turns on the Unicode. So from there, I was able to see immediately all the file information. So I get to see the company name and all. But the key thing of interest for me was the product name, and it says visualstudio.net. So I just took that literally as it is, and I wrote a rule down here that says that it must have the product name, and it has a .net. So the key difference is I put a white and I put it as a full word. So I guess this is actually a really beginner's approach. So from this, I was able to run the rule on the collection, but I only got 3 files instead of 4.
No, no, that's actually correct. It's in total 4 files. You have the
In total, 4
exercise
files.
file, yeah, and the 3 files from the collection. That's very good. Thanks for sharing.
Sure, no
Um,
problem.
I just want to add a few things. Let me share my screen. Um, Okay, so I have the exercise file here. Let me show you. Let me show you this again. So I have a strings and I run it on exercise 2 and I get this all the strings that JH also showed. Also with the grep that I showed here, inside this double quotations, you can actually put some words or some characters. You can put .NET here, and with this that dash I that I have added here, it makes it case insensitive. So if it's .NET in capital letters, it will also be found. So basically, there's nothing in the ASCII strings. Also, like your friend shared, but let's add the dash el for strings in Linux. You can add dash u for strings in Windows. When I do this, I find the exact same string. So if you remember yesterday, I mentioned that every rule that works is good enough. There are many ways to write a rule to catch a file, and it's up to you how to do it. But the differences are that you might get more false positive, you might get less false positive, you might write a rule more strict and actually miss some files that could be matched. Um, anyway, it's up to you. For me, I would use the exact same string to make sure that it's not just .net. .net might be like at the end of a URL or something else. But if you have Visual Studio.net, um, that might be a bit more specific. So let's try writing the rule together. I will name it .net .yara. So rule .net modules .net module. I'll skip meta section and just put strings, and then we can have a equals let me actually try the strings dash el on exercise 2 grep dash I .net again. I'll copy, select the string and put it here. Because it was a Unicode string, I add wide, and then we only have condition, and the condition would be a. So let's see if it works. YARA-R.net. So we found the 3 files that was also catched by JH YARA rule, and the exercise file itself. No more that. So of course, these files have a lot more strings in common. Any of them that you add to the conditions, that would still work. You can even have only like .NET here. That would also work. But if you make it any less strict than this, you might find other files in the collection that are not relevant as well. So any questions? Anything is not clear? Oh, Frankie says that the -el switch didn't work for me on macOS. It might actually be different on macOS. Sorry, guys. I haven't checked everything on macOS. Might be different. You can try looking at the manual of strings with the command man strings on your Mac. And in the manual, you can try to see which option works for Unicode strings. That's how I work with different applications and utilities when I want them to do something specific, when I want to see what are the options. I look at the manual and find what I'm looking for. So do you guys want to try writing the rule and checking the exercise again yourself, or you want to move on to next exercise? Just a few of you let me know and we can move on or continue spending a few more minutes on this exercise. So with the Windows, have you tried extracting the strings from the file and from the archive that I shared? You need to run the strings.exe in a command line, command prompt. Okay, any more questions? Just let me know if everything works in your environment, if the strings works, if YARA works. I'm sure YARA should work because we have worked with YARA yesterday, but if a string doesn't work, let me know. Um, we can try to fix it. So anyone has managed to use the strings tool that I shared on Windows? Because there's at least someone that hasn't managed to use the strings that it works for me on Windows. Okay. So yeah, I guess you just need to run a command prompt and use that to run a strings. It's again a console application. It's not a it doesn't have a GUI. Okay, let's move on to next exercise if you don't have any questions about this exercise. Okay, next exercise with the file that you have, exercise 3. First of all, um, with the compiled applications, sometimes there is the debug details that are left in the files. It depends on how the file is being compiled, if it was compiled in the debug mode or uh, if it's compiled in the debug mode, sometimes the debug information is left inside the binary. And this is actually very useful when you do malware analysis. If by mistake the malware writer has left the path of the project in the um, debug section of the file, it can be really helpful because most of the times it shows the project name, it shows the module name of the application, and you can easily use that string to find other applications from the same project, other examples of the same module, other files that might be compiled on the same system. So this PDB path or project database path is a very useful information that can be found sometimes inside the binary. Uh, with this file, even though it's not a malware, there is the PDB path left inside the file. I want you to find the PDB path and then try to write a rule to find other files from the same project path. There should be 9 files in total, like one is the exercise 3 file and 8 other files in the collection. That's the first part of the exercise. The second part, we want to restrict the rule to find only this specific module, not every file from the same project path. Only this specific module, but it could be compiled for different platforms. So yeah, regardless of the platform. And there should be five files in total. Um, there's also a hint here for the second part, um, that with this specific module, there are different source code file paths found in the module, and it's not only the PDB path. So yeah, let's try. If it's not clear, let me know. I can explain further. If it's clear, um, I guess maybe 15 minutes um, should be enough for this exercise. Let's work on the first part first, and then we move on the second part. I mean, third part. Has anyone found the PDB path inside the file? Okay, great. So if you found the PDB path, that should be easy to write the YARA rule, right? So make sure that for the first part, we want all the files from the same project. And with the second part, we want only this specific module, not every file that was in the same project. We want this specific module, but we want it to be found regardless of the platform that it was compiled for. So for those of you who have not found the PDB path yet, try looking for a string that ends with PDB. That's the PDB path that is left inside the binary. When you find it, you can see that it has the path of the project and the module that was compiled on the developer system. By the way, I forgot to ask you this. All of these files are portable executable files for Windows operating system. And we've already seen how to look for the magic header of MZ in the file. Try to add that condition to your YARA rules as well. To make it more specific, you are not looking for text files or any other file formats. You are actually looking for executable files, PE files with that specific strings inside. And let me know how it goes. Any luck with the YARA rule? Anyone has managed to write the YARA rule? Let's try to make sure that first of all, the YARA rule catches the same binary file. If it does that, then we need to modify it to make sure that it catches other files from the same project path. So yeah, first try to make sure that your YARA rule catches the same file that you are working on. Okay, guys, if you have syntax error, that might be because you have not escaped the slash in the path. So for each slash, you have to escape it with another slash. So you need two slashes. Any luck? Anyone has managed to write the YARA rule? As I said, make sure that you escape the backslash in the file path. So let's go step by step. Let's see who have found the PDB path. Let me know in the chat. Okay, good job. Some of you have found the YARA rule. The rule okay for question 2. That's great. So for people who have not found the PDB path, have you tried the strings and pipe it to either find a str or grep and look for PDB? You should be able to find the PDB path inside the file. You can try it together, but because some of you are working on the second part of the question, let me give you a few more minutes and then we can work on it together. But in the meantime, please try to look for the PDB path inside the file. Okay, let's try to do it together. Is anyone um, does anyone want to share their screen and show how to find the PDB path, or should I do it? I prefer if some of you are comfortable to share your screen and show the others how you found the string and write the YARA rule, even if it's not working very well. Um, it's good to share. So what does it mean by regardless of its platform? So when you look at the PDB path, you can see that the file was compiled for a specific platform, like for x86 platform or something like that. There are different files, um, different examples of the same module in the collection that are compiled for different platforms. So some section of the PDB path is different, but the module name is the same and the project name is the same. Um, this is a hint. You can either use like different parts of the PDB path, or you can use the hint that I have given you on the screen. Uh, you can see that with the exercise file, you can try and see that there are a number of source code file paths, not the PDB path specifically, but the source code paths inside the file. And with this module, other examples of this module have the same number of source code file paths inside them. You can use that characteristic to make the rule work. Okay, let me stop sharing this screen and show you how to find the PDB path.
I know, Shin, maybe I can share. I don't mind
Sure,
sharing. Yeah. Hold on.
sure, please go ahead.
Yep. Can you see my screen?
Yes,
Yep. So I have a few panels. Referring to the top one. Yeah. So I'm passing strings. With the exercise tree. Looking for PDP. PDP. Yep. So after running, I will see this string. Um, which is the PDP path. So here we see the path uses WinSign projects with a module. Then for the rule, part one is this is the answer to question two. So basically, I put in everything until the source, um, and I do a no case ASCII, and I managed to. So let me do that first. Give me a while. Yeah. So I'm looking for the magic header here as well, and for this particular string, I'm looking for this path. So let me save it and let me run it. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9 files. Do I go ahead with the part 3 one?
that's great. So let's see if anyone has any questions so far
Okay.
with the part one. Any questions? Uh, is it clear for everyone? That was the approach. That was the right approach. You find the PDB path, you look at the project name, and use that project name to find other files. You can actually look at, try to find that specific string inside the files, inside the files that are matched with the YARA rule, to see what are the PDB path of that modules. There's actually an option that you can use with the YARA scanning. That option helps to show the exact strings and the offset of the strings that are matched inside each binary, which is -s. If you use -s, you can find this, the exact offset of the strings that are matched. Then you can use that string, that offset, or you can use that binary file again with the strings and with grep to see what was the full path inside that binaries. So, any questions? So yeah, please proceed with the next part. We would
Okay.
love to see how you worked on it.
Okay. So the second part is to look for regardless of the platform. So here we notice that there is this x64, which means that this sample was compiled for 64-bit. So basically what I do is I think it's the lazy way. So I match all the way up here, but I ignore the x64. But I put another module that includes the exact open VPN connect.pdp, and I basically search on all of them, including of this, ignoring the x64. So I save it and I run it. This time around I have 5. Yeah, that's all.
That's very good. Thanks for sharing. Um, it's great. Let me show you how to how to also use the hint that I have provided here. So let me share my screen. Um, so this is the exercise file here. Let's look at the strings from exercise 3 and try to look for PDB path. So this is the PDB path, right? As I said, this module has more than one path to source code files inside it. Let's try to see how we can do that. Maybe look uh, for the project path like this. Instead of PDB, let's try to look for, sorry, let's try to look for, oops, sorry. Just give me a second. Let me check what I've done wrong here. Do you guys see any typos? Maybe I only look for okay. So as you see inside the file, there are a number of similar file paths, but these are not the PD. There's only one PDB path here. These are other source codes like C file from another module, device.c, rxpath.c, and so on. So if you run your YARA rule based on this project path, which I will create a rule now to work with it. Let's see, PDB path. Let's write the rule PDB path, strings A. As I said, we need to escape the backslashes inside this. Okay, what else? I asked you to add the U int 16 at offset 0, 0x5, 5a4d, and string A. Okay, let's see. YARA-R. So now we have the 9 files, right? But if we add another condition here, if we add another condition to make sure that the number of the count of this string inside the file is more than 1, or if you want to be more precise, it's actually 246. We can find only that 5 specific files. We can add the string like the open VPN, tap open VPN as well, just to make sure that it's more strict and it doesn't catch any false positives. So this one, let's do and B. So we learned how to look for the number of strings, right? If you use the number of strings, you actually don't need to ask for the string to be there again, because that also implies that the string is there if you ask for the number of strings to be more than 1. So this is the number of occurrences of this string. If you say this equals 6, let's see how it works. If we try YARA again, you can see that there is only these 5 files. So let's actually try to look at one of the other files to see if the PDB path was actually different or it was the exact same. Let's try this strings. This one, grep PDB. So as you see, this is a different path with the first one here. We had the source x64 release, but here we don't have the x64. Or let's try another one, strings. This is similar to our file. Maybe this one. This is similar to this one, and also another one. Check this one already, the last one. This is also similar to our file. So that's it for this one. This is actually not the best rule that we can write for this file, but based on our knowledge so far, this is quite good. We are actually going to work on the same file and the same YARA rule later tomorrow um, to make it more accurate. So I guess stop sharing. We have only a few minutes left, so I guess I don't continue with the slides. Let's see if there's any questions we can answer in this 10 minutes, and then we have tomorrow to work on further more advanced techniques and extra modules of YARA. Any questions? But actually, if there is no questions, we can proceed to look at something else. Not an exercise, but a little bit more information about the strings and conditions. No questions? All good? Okay, great. So I know it's end of the day. It's almost 7:30 to your time zone. It's 10:30 p.m. at my time zone. I'm based in Australia. So I'm not going to bother you with another exercise. Let's continue with something that we are not going to use in exercise, but these are some like extra information about the strings that you can use later in your work when you work with YARA. So first of all, YARA also supports hexadecimal byte sequences as strings. We have already seen this. Something like this. These are like hexadecimal values, and I said that it's these are used in the curly brackets. We can also use these question marks to make sure that anything that is there at that specific offset of the string is matched, and we just ignore that part. We can also use ranges to show that at this part of the hexadecimal string, we want anything between 2 bytes to 10 bytes. This is the size of the substring here. We can also use like different options for sequences, like this would actually match 0, 1, 0, 2, 0, 0, 3, 0, 5, or 0, 1, 0, 3, 0, 4, 0, 5. These two options. Also, looking at some code here, not sure how familiar you are with assembly code, but this is like a more advanced way of using YARA rules with specifically for malwares. Again, as I said, most of the times these are like the strings that that form the unique patterns inside the files. In most of the cases, you might not need to do reverse engineering or look at the code of the file. Only the strings could help. Strings and metadata of the file combination could help to write a good YARA rule. But of course, with more sophisticated malwares, with more advanced attacks, you may need to look at the actual code and find something inside the code, like a decoder routine or something like that. I'll talk about it later as well. So I wanted to share some example here, some example of the assembly code inside the file and the hexadecimal values of these operations. Here we have the hexadecimal values or opcodes. These opcodes belong to the instruction that is how to say the assembly instruction, and also the operands. Like this one, this is a XOR instruction with a register name and some constant value. And here you can see that this 80, the hexadecimal value 80 belongs to XOR operation, and then F1, 3F, this belongs to the CL and 3F hexadecimal values. So as I said earlier, we can ignore some parts, and it's very important to do it sometimes because when you look at the code, you have the name of the register sometimes like CL, BL, EDI, EAX, EBP. These are different registers, CPU registers, and you actually have some constants and also some specific addresses or like relative addresses inside the code. And depending on the compilation environment, these could actually change, and it's very common that they change. Like you might find another sample that is exactly the same, that is compiled from the exact same source code, and the registers that are used for different instructions are different. So we want to make sure that the rule is generic enough to catch all the samples of the same malware. So we want to remove all these parts that are um, compilation environment related, and only keep the hexadecimal values that are related to the instructions. So we just change them to question marks. And also in some cases, in some instances of compilation, some of these values might be different and have like different lengths. For example, with this push 0, it might be different, and it might not be 0 in another case and might be like longer. So we need to make sure that this is not only like 1 byte, it might be longer than that. Like for example, first of all, I changed them to the exact same size, and then you can change it to ranges. Like for this one, this is a XOR key that might be more than 1 byte in some other examples. That's why we change it to 2 to 5. And this one also, this is a constant as well. It can be something different. So with all of this, we can create a nice sequence of hexadecimal values that can catch files with similar routine inside their code. Also, apart from the hexadecimal values and the plain text that we have seen already, you can actually use regular expressions in the strings. With the regular expression in the YARA engine, YARA uses its own regular expression um, set of patterns. It's quite similar to the Perl compatible one, but some parts are not there. So make sure if you want to use it, you check the exact specifications, and you know which parts are not defined in YARA. Like for example, the groups are not defined, the back reference is not defined in YARA, but some like basic regular expression patterns are defined like this. You can create pattern that matches every MD5 hash value, which consists of digits from 0 to 9, and alphabet characters from A to F that could be lowercase or uppercase, and it's always 32 in length. Next, this is actually very important. What kind of strings to look for when writing a rule? we have tried a few exercises today, but to be prepared for real life exercises with YARA rules, you need to know what strings to look for. In our exercises today, I have provided some hints, like look for PDB path, look for a string that shows the file belongs to .NET environment, something like this. But when you don't have any clue, um, it's a bit more challenging what sort of strings you can look for. So I have categorized it into a few classes. Like first one is text strings. You can look for file names and extensions. You can look for export names in libraries. You can look for URLs, domains, IP addresses, emails that are left inside the code. You can look for mutex names, even names, pipe names. Also, grammar mistakes are very common in malwares that are written by non-English speaking cyber criminals or malware writers. You can look for program commands and options that are left inside the code by mistake or are present in the code as the logic of the code. You can look for error and confirmation messages. Also, some implementation traits. You can look for compilation timestamps. You can look for mangled class names, certificate details, compiler and linker versions. You can look for memory allocation habits, a bit more advanced. You can look for construction designs, which are quite unique to the developer of the file. You can look for dynamic API loading techniques, which is very common in malwares. Also, some custom features. You can look for cryptographic keys. You can look for unique string hashes, encrypted strings, string encryption algorithms. You can look for domain generation algorithms, also common in some malwares. You can look for string hashing algorithms or obfuscation techniques. And this is good news for the last minute of our session, that these ones that I highlighted, these typically don't need reverse engineering. So with all of this, you don't need to do any reverse engineering. You can just extract them using strings, using like PE viewers, and with the other ones, you might need to do some reverse engineering. So that's it for today. Tomorrow we are going to look at some extended conditions, and then continue with looking at different modules that are defined for YARA to help um, do the pattern matching and matching with the different metadata of the file much easier. Any questions? So please try to do the exercises that we did today. If you haven't managed to do it, I'm sure it won't take more than a few minutes of your time. But if you can do it before our session tomorrow, like maybe 10-15 minutes before our session starts, you can just try to do that exercises. You will be more ready for tomorrow. Again, like today, we won't have many exercises. It will only be a few. And I hope you have enjoyed our session today. Any questions? So I guess there are no questions in the chat. I guess I'll see you all tomorrow. Have a nice evening. Take care and bye-bye.